To give motivation as to why we should study limits, let's consider a situation where a ball is being dropped from a tall place. Its distance that it travels after t seconds is given by 4.9 t squared, and we want to know the speed, or velocity, at t equals 5 seconds. It might not seem so hard to figure out at first, but it's actually tricky because what we want is the speed at precisely t equals 5 seconds. Now, speed is given by the distance traveled divided by the elapsed time. So what we could maybe do is consider calculating something like this, which would be the distance traveled between 5 seconds and 4.9 seconds divided by 5 minus 4.9 seconds. So this would be 48.51 meters per second. I forgot to mention that this is the distance the ball traveled in meters. Okay, so then is this the speed at t equals 5 seconds? Well, in fact, this is not, because this would be the average speed between 5 and 4.9 seconds. This is not the instantaneous. In fact, why don't we just choose a different number besides 4.9? For instance, something like 4.99, which is even closer to 5 seconds. Then, if we calculate this out, we'll get 48.951 meters per second. This is still not the instantaneous speed, or velocity. This would be the average velocity between 5 seconds and 4.99 seconds. But we can see that if you calculate this number, but with this 4.99 getting closer and closer to 5, then this number will be approaching 49. And so the number that a certain expression approaches will be the limit. So in this case, we can guess that the limit as a approaches 5 is 49, and this will give us our instantaneous velocity. Let's look at another example. For instance, the limit as x goes to 1 of this expression, 1 over 1 plus x. Let's first graph this. This is the transformation of the 1 over x graph, and so there will be a asymptote at -1, and then at 1. This will be at the value 1/2. Now, the limit is what value this expression is approaching, and we can see from the graph that at both sides it's approaching this number here, its value. And so we just plug in 1, and we can see that the limit should be 1/2. Now let's try another example. The limit as x approaches 1 of this expression. This expression we can simplify a little bit. This is by factoring, we can see that this is x minus 1 over x minus 1 times x plus 1. Now it's important to note that this is not equal to the function 1 over x plus 1, because this is not defined when x equals 1, but this expression is defined when x equals 1. They are very close to each other, but we cannot cancel these out. We can only cancel them out when x is not equal to 1. So the graph of this function will look like this, but it is not defined at x equals 1. But we can still find out what the limit is because we care about where it's approaching. And from both sides, this is approaching this number here. So even though it's not defined, it's approaching this number 1/2. And so the limit of this expression is 1/2. Now let's consider the heaviside function, and let's consider the limit as x goes to 0 of h of x. The graph of the heaviside function would look something like this, where for negative values of x, it's 0, and for positive values, it's 1. Looking from this direction, it's approaching 0. From this direction, it's approaching 1. So these are different. So this limit, we say, does not exist. But we can say something, namely the one-sided limits with the minus sign. The limit as x goes to 0 from the left, which is denoted by a minus sign of h of x, means you're looking at values less than 0. So from here. So here it's approaching 0. And we can also ask what the limit as x goes to 0 from the right, or larger than 0, is for h of x. So that's going to be from this side, which is 1. So the one-sided limits exist. And then a fact is that the limit as x goes to a of some expression exists if and only if the left and the right-hand limits are equal and they both exist. If the left and the right-hand limits both exist and they are equal to each other. So if they're different, then the limit does not exist. Now let's go over some basics on how to calculate limits. For instance, this limit, one thing you can always try is to simply plug in the 1, but in this case you'll get 0 over 0, which is undefined. So we need to use some algebra to simplify this expression. So as before, we can factor. Now remember, we cannot simply cancel these out, but we do know that this expression is equal to x plus 1 when x is not equal to 1. Now when we are taking the limit, we want to know the value when it's approaching. When we say it's approaching x equals 1, well, that means it's not x equals 1. So x does not equal 1. So actually in the limit, we can say that these are equal. So while the expression by itself is not equal, in the limit they are equal. And then here we can just plug in, and so the limit is 2. So if plugging in does not work, then you have to do some algebraic simplification. Let's try one more example. Let's consider this limit. Again, if you plug in 0, you will get 0 divided by 0, so it's undefined. So we need to take a similar strategy to compute this limit. Now, whenever we see a square root, one good idea is to multiply the expression by its conjugate. So we take our expression and we multiply by its conjugate so that we get t squared divided by t squared times square root of t squared plus 9 plus 3. Now, remember, we can't just cancel these out, but we are taking the limit, so in the limit they will cancel out. So we get that this limit is equal to the limit as t goes to 0 of this expression. Now we can just plug in t equals 0 and we'll get 1 over 6 as our limit.